And I have a studio audience today. Everybody, yay, hurrah, yeah. Yeah. Okay, it's early in the morning. I got a sleepy studio audience. We're going to do a few of these help videos today. See, this means we can get done. These are called Girl in the Jeep problems because it's a girl in the Jeep. I can change her car to make her the girl in the Corvette, but the Corvette doesn't show really when she accelerates. The car kind of comes up. When she puts in the brakes, the car leans forward, and the Jeep shows that better. So I always call her the girl in the Jeep. All right, and what we can do on this graph is I can show her here the velocity versus time, and then from there this will grow. This is displacement versus time, and we call these trios in my class. And so this is x versus t, this is the v versus t that corresponds to it, and there's an acceleration versus time, which in this case is pretty boring. It just has an acceleration, which is the slope of this line. So it'd be 60, rises 60, runs 10. So it'd be the slope of that line. So it's 6 meters per second, because this is meters per second on this axis and seconds on this axis. So you'd have, for acceleration, you'd have a flat line down here that is at 6, and then it goes to 0, which means there's no slope, no acceleration from 10 seconds to 14 seconds. Okay, so I don't know how well it comes off on the camera, but here's the speedometer, and this shows her position, okay, as she goes. So we'll start off with a fairly simple one. Looks like she's going to speed up for 10 seconds, go from 0 to 60 meters a second. Well, 60 meters a second is pretty fast. I think that's 60 meters per second is that's 0.6 kilometers, 0.06 kilometers per second. That's so many miles per hour that is. 0.06 kilometers, right? There is 0.06. 0.06 kilometers per second, then times 3,600 seconds. So that's 216 kilometers, and then divide that by 1.6. So that's 135 miles an hour. So she's going to go from 0 to 135 miles an hour in 10 seconds. So that's a heck of a Jeep. All right. So here we go. I'll push the little start button here, and I'll be stopping it just to see what she's doing. Okay, so when you hit the start button, I'll start it and pause it. So watch what happens. I start it, and now we're moving along. Now I'm going to pause it. Now notice the Jeep is kind of angling upwards. That means she's accelerating this way. When she goes at a constant rate, which she will here, the Jeep will go back to horizontal. And I doubt this picks up on the camera, but there's a very light green line that says where you're at along her path. So far she's at about the 18 meter mark. Let's keep going. And watch her, okay, we'll go back to the beginning. Watch her speed. It grows and grows and grows until it gets to 60. Then it's going to stay there. Notice she's angling up. And then right here, it goes horizontal again. What happened? Oh, I must have hit something. Well, anyway, there she goes horizontal. And she stays 60 the rest of the time. So at 10 seconds, she went horizontal and then stayed 60. So she ended up at 540 meters away from the beginning. And is there any way that we could have determined that without any kind of equations? Anybody in the studio audience want to offer? How could we have determined that she's going to end up at 540 meters?
The area under the graph.
Okay, so for v versus t, we can look at the area under the graph, and I'll get to this in a second. But if you'll take this area, this is 10, so it's 1/2 base times height for a triangle. The height is 60, so half that's 30. 30 times 10 is 300. So at this point, when she got to the 10-second mark, she'd already gone 300 meters. And then you add on this area. This is a rectangle. It's 4 by 60, so that's 240. So when you add 300 to 240, you get 540. So very good. And then also notice, as it's displacement graph, what I have the students do, and what you ought to do on the next one at home, if you're watching this, is you ought to predict. I'll give you a velocity versus time graph, and you'll have to predict, or I want you to predict what x versus t will look like, and then we'll see if you're right. Now notice in this case, that was linear with a slope. Well, if that's linear with a slope, that means this is parabolic. And we've learned that in class. That's called the trio. And so if you have flat for acceleration, linear for velocity, that means parabolic for x. It's parabolic until you get to the 10-second mark, and then, unfortunately this doesn't show time, but at the 10-second mark, then it goes linear because this becomes flat. And so as you go from here to here, this is the slope of that. All right? Or in calculus, this is the graphical derivative of that. And that's all slope is derivative. If you're in calculus and you've gone this far, this is the integral of that. And that's why we said the area under the curve. Okay, so there's your first one. Now let's throw another one at you. And this time, I'm going to have a situation here. This time I want you to make a prediction. If it's 2010, there might be a worksheet on this. If it's 2009, all you got to do it on a piece of paper, do it in your notebook. But I want you to predict what displacement versus time looks like. It's a lot similar to the one we just did when it went up and came over. Now it's going down and comes over. And I guess the question is, if I were to plot the acceleration versus time, that'd be, I do slope graphs below, and acceleration is the slope of velocity. So I would start off with a negative. That would have a negative slope. It's looks like it drops 60 over 12 seconds. So what is it, negative 5? So negative 5 meters per second would be the slope to begin with, and then the slope goes to 0. All right. So I want you to do two things I want you to push pause in a second. I want you to predict what this graph will look like, sketch this graph, and then I want you to predict where she ends up, how far away. And I know it may be hard to see, so let me describe this. She goes from 0 to down to negative 60 and does that in 12 seconds. And then from 12 through 17, she stays at negative 60. Okay, so I'll give you a second to predict what it's going to look like and predict, make sure I'm on here, and predict a final position, final negative position. Okay? Alright, so we're back. I hope you did try it. Let's see if you're right. Okay, so there's, it's not starting. There we go. So she turns around, backs up. I'll put it on pause for a second just to show you. She's going kind of slow. But she's starting off kind of slow. You can see that she's backing up. The Jeep is a little bit tilted. Her hair is coming back. So she's right here along the path. She starts off slow. She's getting faster and faster. Remember, she's going to go up to negative 135, somewhere in there, 132 miles an hour in 12 seconds. Then she'll maintain that speed. So notice this graph, if that's going to be linear negative, this is going to be parabolic, but notice it's starting to come down, starting to curve down. And we'll keep going. And her speed is in reverse. That says reverse there. So see, we're still in the parabola, and now linear the rest of the way. It maintains that last slope it had, and it keeps that slope the whole time. Okay, so if you predicted that, and also she ended up at negative 660, that would be the negative, what a calculus teacher would call, calculus call these signed areas. That would be the negative area here. You can have negative area on a graph. Okay, so you're getting the hang of it. Now, when I come back, I'm going to have a little tougher one. It's a little tougher. Now we're going to combine this. We're going to go to we're going to start off 0. She's going to have 0 velocity. She'll go positive 60 up to positive 60. It takes her 6 seconds, and then she'll go to 12 seconds. She'll be slowing down. Now, a couple of questions, and this would be what you would see on an exam, is I would ask you, I might circle, I'm not sure I'll do this, but I might circle that, and that, and say, what is she doing at this point, and this point? Well, here obviously she's just starting 0 velocity. But if I were to ask my now very small studio audience, if someone could tell me what is happening right here at 6 seconds.
Slow me down.
So she's starting to slow down. She was speeding up, right? So as far as her in the Jeep, is she turning around there?
No.
And why do you say no?
There's no negative slope.
So well, there is a negative slope there though, isn't there? Isn't there start off positive slope and then goes to negative slope? So, keep going.
There's no negative velocity.
So you're saying the velocity's in the first quadrant the whole time, so it's positive. So as long as velocity is positive, she's going forward. Well then, what's the deal with the negative slope then?
It's just slowing down.
Okay, so what is negative for this part? Not the velocity, what is negative?
The position.
Now wait a minute, we'll get to position.
Acceleration.
But acceleration, right? Acceleration is positive until you get to 6 seconds, and then acceleration becomes negative. Does her position ever become negative? She's in the first quadrant, so she should stay, because she's always going positive. On your prediction, you should predict her to stay in the first quadrant the whole time. She'll never go down in the fourth quadrant for this graph. And one last thing, we call this a special name from math. And what name would this be? What would this? It's a relative maximum here. I know it's a deflection point, but it's a relative maximum here on the v versus t. What will this translate to on the x versus t? We mentioned this the other day. Point of inflection. So this, in other words, that's the point of inflection on a graph is the steepest point on the graph. So whenever you're plotting that, make sure that you start off with that's zero slope, it ends with zero slope, but in the middle it has the most positive, steepest slope. So I know I got flat, steep, flat again. So what letter would that make? Yes, isn't an S flat to begin with, steep in the middle, and flat at the end? So now you pause it if you need to, but let's make your prediction, and here we go. We're back from your pause. Alright, so she's speeding up, speeding up, speeding up, speeding up, and right, if I can get it right there. Okay. She's still speeding up. I just went to the slowing down. So her Jeep went from this angle to this angle. So she was speeding up, speeding up, speeding up. So at this instant, at 6 seconds, that right there is the steepest that slope's going to get, because that's what that's telling me. Very steep positive slope. From here on, the slope is going to become less and less until it becomes flat. Okay, and her speed's at the maximum, 60. Okay, and now notice she slows down. This thing is the point she's slowing down, slowing down. You can watch her slow and finally stop. And it's weird because she stops instantaneously, because this is not really a very authentic graph, because there's no way you can change speeds that fast. And there's our S. It's very elongated. But if I make that real steep and then make it come down real steep, I can make that look more like an S. But I've stretched it out over 12 seconds. Okay, we're not going to do that. Okay, we'll try another one. All right, here we go again. Now it gets more complicated. I want you to plot what you think it'll look like. Start off with zero velocity, as we always do. There's the key parts of the graph. If you were to plot this, which I wish you could do this, but it can't on this program, and put it above, then you'd have zero. You have we saw it yesterday or last time. That's an inflection point. There's a negative inflection point. This means it's the positive steepest it gets. That means it's the negative steepest it gets. And then right in here, the question is what's happening there. I want you to think about that. And then you end up back at stopping again, so it's zero slope. So pause this, and I'm just going to pause this and predict what you think the displacement versus time will look like. Okay. Now let's go ahead and run this. And I want you to think about what, I think this is the weirdest part right here. Positive acceleration, negative acceleration that whole way, then positive acceleration. But let's see what it looks like. Okay, so here we go. We're going up to that point of inflection and reached it. So now we're at the steepest part. It'll never get more positive than that, more steep than that. So now we're going to start to head back down. The slope, remember this graph tells you the slope. So the slope must be 0 there. She must not be moving. Okay, see what's happening. Okay, so right there, okay, she just passed it, and notice what happened when she got to there. She came up, and this point then is a maximum. It's starting to head back down now. So whenever it crosses that 0 point, going from positive to negative, it becomes a maximum. So those stand for turnaround points. Alright, so one studio audience is leaving and the next one comes in. I'll keep going. Thanks guys. 1 through 3 on that worksheet for Monday. So that's my turnaround point, and then I'm going to keep going. This will be a negative point of inflection. So this graph will not look like an upside down parabola, because an upside down parabola wouldn't have these inflection points. So let's keep going here and see what happens. So there's your negative inflection, and now it's going to come back, and it should, if I did this right, come right back to where she started. Because the positive area of this triangle equals the negative area of that triangle. And so we get a nice bell-shaped curve. Okay? So if you predicted that, that's great. We'll try another one. Things. First I want you to predict what this graph will look like. And then I want you to predict where she ends up. Now let me give you some numbers here. We start at 0. If you can't see this, it goes down to negative 60 meters per second in 5 seconds. It comes back up, and it looks like at about the 8-second mark, you're back at 0 velocity. And we know now that's a turnaround point. We were going to that last one. And we know these are inflection points. And so the steepest negative slope, that'll help you. Whenever I'm plotting one of these, when I'm up here, I go, okay, flat, negative, flat, positive, flat again. If you have those points, you can then plot your graph. So she's back at 0 at 8 seconds. She goes to 60 meters per second, it looks like, at 11 seconds. And then she drops back down at 13 seconds. She's back, it's stopped again, so she's back flat again. So look at your areas of your triangles. Also, you should be able to look at the areas of triangles and very quickly realize which quadrant you end up in, whether you're in the first or whether you're in the fourth. Okay, and the thing to look at there is look at how much time she spends, not just time, but also velocity. So you look at the area. Look at the area of this triangle versus this is a negative triangle, versus the area of this positive triangle. Okay, so now pause it and make your predictions, and we'll see. Okay, we're back from paused. Now I have a new studio audience. 2 outstanding young students are kind of half watching. We're at, my classes really aren't that small. There's a big musical going on. So, some students didn't go, so they're hanging out in here. Alright, so here we go.
Yeah.
Recording? Okay. Alright, so that was totally unnecessary, that pause. Well, here we go. Let's see what happens. Watch her go. So she starts, she's backing up. Back up, back up, back up, back up. Inflection point right there. So notice that she was backing up with the Jeep pointing down. That meant she was accelerating, negative acceleration in this case. Remember, when you're going backwards, it's very hard to think in your mind. It's counterintuitive. What's positive acceleration? What's negative acceleration? Let the graph tell you. That's a negative slope, so she started off going negative acceleration. And this is weird. This is a weird part. Let's go a little further into this. Okay, during this part, right there, she is backing up, yet her acceleration is positive. So that's strange. And even weirder, she's slowing down. She has positive acceleration, but she's slowing down. That always kind of a mind freak there, because how can that be? Well, if I look at my graph, it's easy, it's obvious. But if someone just told you that, said, yeah, I'm slowing down, but I'm accelerating, you would think they must be backwards. But that can happen. So here she is heading back, and we'll keep going. She's reaching a turnaround point. Those are always turnaround points. And so we know that that's going to be a relative, there's my inflection. So this is a relative maximum or minimum, studio audience. Will that be a relative maximum or minimum? And you can look at this graph, see what's going on.
Yeah, that's who knows.
So because we're going from a negative slope to a positive slope, and if you go from a negative slope to a positive slope, that must be a minimum. Okay, so here we go to relative minimum. And there we go. So now she turned around, there's her positive inflection point, and now she stops. And bingo, she ended up in the fourth quadrant because, as you probably noticed, the area of that triangle is greater than the area of that triangle. And so you get that, it looks like a bell-shaped curve, but just not quite finished. Kind of like the bell-shaped curve we just showed earlier. But that was a perfect bell-shaped curve because both triangles were congruent, or were similar. Not just similar, they were the same triangle. Just one positive, one negative. So we didn't quite get our full bell shape, but that was expected because it just didn't have enough positive area. Okay, and if you predicted that she would end up at negative 90 meters, that's correct. And you get that value from looking at, and this is kind of a weird thing. This is a case where area equals length. So tell that to your 5th grade math teacher. Area equals length because the area is meters per second times, meters per second times seconds. So when you multiply those two, you get meters. So the area of this equals length. So I take the area here is negative, the area here is positive. When I put them both together, apparently this is 90 meters greater in area than that is. Okay, so that's what we call the girl in the Jeep. Okay, we'll do one more funny one and then we'll be done. Oh, you think you're smart? Plot that. Yeah. Maybe you can look at it and tell me at least whether she ends up in the 1st or 4th quadrant, and that's just by looking at areas. So their area, that area, I don't know if I can mark on this. That area, that 1, 2, 3, tiny area, 4, tiny area, bigger area, tiny. What do you guys think? 1st or 4th? Is there more positive area or negative area?
It's positive.
Definitely looks like big triangle. There's 1, 2, 3, 4 positive triangles, 1, 2, 3, 4 negative triangles, but it looks like the positive triangles are always bigger.
Oh, yeah.
So we know she'll end up. We got a lot of inflection points, a lot of turnaround points. Starts off with these are all flat, 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 flat. A lot of flatness, but steepest positive, steepest negative, steepest positive, steepest negative, back and forth. Okay. So if you want to, just for grins, you can go ahead and pause it and try and predict. Otherwise, this will not be on the test. Otherwise, am I on? Or am I still
You're recording.
No, oh good. That's good. I want to repeat all that. All right, here we go. Up, down, back and forth, flat, 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 flat. She's getting dizzy. So, sure enough, boy, I just kept on trailing off, but she kept getting more. Because see, the thing is, you accumulate area as you go from left to right. So she kept accumulating that, even though they weren't as big peaks, she already had a lot under her. Sort of like the Dow Jones Industrial, you know, it might gain a little bit, but it already has 10,000 points underneath it. So little bits of gains still add up. So anyway, that's where she'll end up. And she ended up at about 63 if you had bothered to do that. All right. See you next time.